So welcome to the most interesting, coolest and frankly sexiest track here this week, where you will learn all things you need to know and maybe even a few things you didn't about confidential computing. So my name is Mike Bursell. I am the Executive Director, that's what ED stands for, of the Confidential Computing Consortium, not the Chaos Computer Club. Although that would be an interesting job, thinking about it. I am ex-Red Hat, ex-Intel, ex-Citrix, ex-startups, lots of things. And I'm a security geek with delusions of management. So my background is on the tech side. It's one of the difficult things to do when you sort of say you're going to do a technical introduction to anything. Is to know what level. So we've got half an hour. I'm going to get through what I can. I'm going to try and leave time for questions. If you've got clarification questions as we go through, please raise your hand. It's a small enough number that we can do that. And I'll be around for the rest of the day for questions. And you can find me on LinkedIn. It's only me with that name, I think, there. So this is kind of what I'm planning to talk about. First is ways to think about confidential computing. A little bit about the primitives that CC, confidential computing, provides you. A brief description of whether you should be thinking lift and shift or design for confidential computing. A few use cases, and if you're interested in use cases, I'm going to be doing a whole bunch more later in the day after these nice gentlemen from Red Hat have their session. Do stay for that as well. Then just thinking a little bit about new architectural patterns. If you're a techie, then patterns are something you should know about. I'm old enough to have the Gang of 4 book, Gang of 5 book. Who else has the Gang of 5 book? Just one. That's really sad. Anyway, look it up, Patterns Gang of 5. And then I'll give you some information about how we get started and stuff like that. So, I don't have a clock, so I'm just going to take my watch off so I can see how we're going. There we go. Okay, so ways to think about confidential computing. So this is the official definition for the Confidential Computing Consortium. This, minus one word, took us about 6 months of work. That one word is attested, which took another 3 months of work, a year and a half, 2 years later. It's the protection of data in use by performing computation in a hardware-based, and that's really important, a tested, trusted execution environment. And we're going to be talking about a number of those words as we go through. But this definition excludes technologies where that isolation is provided not by the hardware, but by software implementations. And that's really important. So these are chip-level technologies, chip-level instructions, which need, of course, to be turned on in the firmware, microcode, and software stack. But their protection is provided by the chips themselves. So a few things that CC is and CC is not. So first thing is it's available from multiple vendors. I'm not sure there's any RISC silicon out. There is ARM silicon out. IBM have an interesting set of things, but the main ones that you'll see mostly at the moment are AMD, NVIDIA, and Intel. And they're absolutely available all over the place. In the public cloud, again, pretty much every public cloud you can think of has confidential computing available. They don't make as much noise about it as they might do. Maybe they should. It's also in off-the-shelf hardware. If you're buying high-level sort of Xeons or the equivalent from A&D or any of the H or B series from NVIDIA, then they're going to have CC in them. I say all the H. I'm not sure the H for the China market do, but that is the case. The other thing is that confidential computing is part of a family of technologies called PETs. That's not as in pets and cattle, which is too many words. These are privacy-enhancing or privacy-enhancing technologies. Another one you may have heard of would be homomorphic encryption, or things like differential privacy or privacy. It's very performant compared to all of those because of the hardware that it sits there. And also you can use it for general computation. You don't need to be rewriting your entire application to do that, although there's some interesting questions we'll come to as we go. It's not TPMs or HSMs, we should be clear about that. TPMs don't allow you to do general computation, they've got a few capabilities. HSMs, again, tend not to allow general computation. It's also not a single technology, it's a set of different technologies. The way that Intel implements it is very different to AMD's approach, for instance. It's also not just about isolation, although isolation is very important. And it's also not perfect because, well, no security technology is perfect. And it's not just a set of new primitives, although it is a set of new primitives. And I really want to start you, assuming that you're security tech folks, to be thinking about the world in this sort of way. So let's talk about some of those primitives. So the first thing I'd like to do is introduce the standard virtualization model, and this is horrifically simplified, and I apologize for that, but it'll get us where we need to be. So this is how I think of the world. The red dotted box is a computer. It's a host, it's a system, call it what you will. And at the bottom, you've got a host operating system and all the things that that entails. And at the top, you've got a couple of workloads. And the one we care about is on the right, because that's ours, and that's in a little yellowish, orangey, olivey box. I'm a man and not very good with color names. Maybe that's a bit stereotypical, but it's true for me. So that's what we care about, and that's how we think about it. And of course, there's hardware that backs this up, and there's other bits and pieces. But let's think of the world like that for now. And in a standard virtualization model, there were three types of isolation. Type 1 isolation is isolating one workload from another workload. And containers and VMs are pretty good at that, right? We know how to do that, it's not very difficult. Type 2 is host from workload isolation. And again, containers and VMs are pretty good at that. We get the odd breakout of the sandbox model, but that's fine. The problem is that type 3 isolation, which is where the host looks in the workload, is not dealt with at all in the standard virtualization model. In fact, standard virtualization model for both VMs and containers requires that the hypervisor or equivalent can look inside the memory pages of your workload. And that is not great if you want to be isolating because you don't necessarily entirely trust the host or its operating system or the people who run it or the software on it and all those sorts of things. So what confidential computing does is it leverages hardware capabilities to provide what are called trusted execution environments, which basically isolate that workload, isolate those memory pages in RAM so that they can't be looked at. And exactly how that happens depends on the technology, but the easiest way of thinking about it is those memory pages are encrypted. So even if you have kernel access or admin access, sudo access, whatever, or hypervisor access, if you try and access those pages, you will either get a page fault or you'll get gibberish. So there's no way of looking at it. So they're only ever decrypted or accessible when they are being processed by the CPU. So not even on the bus. It's actually on core that they're safe all those times. And the definition used to have words like CPU in it as well, but it's absolutely now in GPUs. We're going to be seeing it in NPUs and any other PU you can think of, frankly. I've lost track of what they all are, but don't think of it as just a CPU thing. It's absolutely a GPU and elsewhere as well. And so the TE does two big things. It protects the integrity of whatever's in it, those memory pages, but also protects the confidentiality through this isolation model. And that's fantastic. But it does leave a missing bit. Because let's say you're Red Hat. I'll just point at a Red Hat person over here. And Red Hat, let's say, provides hosting services. And so I say to Red Hat person, I'd please like you to set up a trusted execution environment on your hosting service. And he says, it's done, and it's ready to use. And I say, that's great. But the whole reason I'm using this is I don't trust him in the first place. So how can I trust him to have told me that it's set up correctly? And this is difficult. So also, he might be using hardware which doesn't even support TEs properly. So I've got that problem. I need to check it's properly set up, and that what's in that TE, what I put in there, is what I think should be in there, not what he's decided to put in there. And also, there are times it's really nice to know that each TE has a unique identity, so I can identify it and talk to it and do nice identity stuff with it as well. And that is not provided by the basic isolation, right? So what we need is attestation, remote attestation. And again, this is how I think of the world, and it's very simplified, and I apologize. And this is just one way of doing attestation. There are at least two, and possibly more, depending on how you think about it. And this, again, is my computer. It's got a CPU and or a GPU at the bottom, and the top bit is the TE, the Trusted Execution Environment, which is hopefully correctly set up. Okay? So what I'm going to do is I'm going to put my TE, I'm going to put my application in there with some data and stuff. As I said, this is one model and it's not appropriate for all use cases, but this is easy to explain this. And what it's going to do is it's going to say to the CPU, which is providing this capability in the first place, remember, please measure me. And it does a measurement, and you can tell it's a measurement. It's got ones and zeros. It's binary, so it must be true. And it's going to sign it, and you can tell it's signed. It's got a little green padlock. And it passes that to a third party, so not run by this gentleman over here. It could be run by this gentleman over here. Okay, so you are a remote attestation service, or an AVS, attestation verification service. And that checks that signature is correct, and what's more, that those ones and zeros correspond to what we think should be in that TE. Got someone from Intel nodding along. That always makes me very, very relieved, I have to say. And then that can be passed to the user, and that allows the user to say, okay, the TE is on valid hardware, it's correctly set up, and what's in there is what I think it should be. Okay. The more perspicacious among you, no, that's a good word, or those who already know the script, will know that there's a bit of a problem in that the confidentiality of what's in there isn't guaranteed in this use case. There are other ways of doing attestation, but this is a simplified version. Okay, so you can absolutely have assurances around that as well. I should add, I may say it elsewhere as well, that thing there, that blue thing with the green padlock, that's assigned data, right? It's basically a certificate. You can make a certificate out of that. We can do all sorts of nice things with certificates, including things like TLS. So we've now built ourselves some really nice primitives. We can also use certificates for things like auditing, which is something I believe is quite important in the financial world. So these primitives, the hardware-based TE and the remote attestation, provide these properties of integrity, confidentiality, identity, and uniqueness. And those allow us to answer some questions. What's running? Can it have changed? Because you can always remeasure or have other controls, like making sure that it can't load other code, for instance, to allow you to answer that question. I'll make all of the slides available, by the way. Can anyone see inside it? Am I talking to this one, the version that I think I should be talking to? And these are really useful things to be able to answer if you're designing complex systems which have important security or privacy or auditability properties, which is why I hope you're all here. Oh, that's another good one. Can it have been spoofed? Can someone have faked it? So this leads me to my next bit. We're about halfway through, which is lift and shift or design for confidential computing. So by lift and shift, I mean take an existing application and create a TE and shove it in the TE. Okay? Absolutely fine. By design for CC, I mean, okay, well, let's think about designing a system which has some knowledge of these properties, the isolation, the identity, or maybe, most usefully, the attestation properties. So here are some of, this is again how I think of it. These are not all of the things. But on the left, we've got some properties we might like to have, and on the right and in the middle, we've got how these things typically look. So first thing is data and use protection. Yes, you get data and use protection for either. This is good, it is important, that's the main thing that most people for now are thinking about using confidential computing for. I have a question, sir.
How can you have data and use protection? I understand that it's encrypted when it's in memory, but when it's actually being executed by the CPU, it's got to be decrypted, and the operating system has access to the CPU.
So the question is, surely the operating system has access to the CPU and the memory? No, it doesn't. The CPU executes the code. So you have the code as part of the memory pages, and so the OS does not have access, in fact, to the data and the code when it is executing. It's one of the big differences between the standard virtualization model, which is an entirely good point and really important to understand. So that data and that memory is only ever being executed in the CPU or GPU, whatever it may be. Thank you. So the next thing is, what does your TCB look like? And typically, if you're doing lift and shift, you're taking maybe a whole container pod, for instance, or an entire, Linux VM. Your trusted compute base is going to be bleeding ginormous, frankly, to use technical terms. And so that's not always a very good thing. However, if you're designing for CC, you can make it pretty darn small. I used to work for a company which went bust, but we did open source our work, where we created a WebAssembly-based microkernel which ran just that. It was absolute minimum. It's called NARCs, if anyone's interested in it, and it's a Confidential Computing Consortium project. So you can make your TCB very small. Attestation is the next thing, and if you're doing attestation for lift and shift, the thing inside it can't understand that it's being attested unless you rewrite it, in which case you've done the thing on the right. Obviously, external parties can be aware of that and can do that, but it's rather more difficult to do internally. Whereas if you design for CC, all the bits of the puzzle can know about it. So the application itself running in the T can know that it's been attested and can present information externally to help with that. Visibility management. I'm trying to remember what I thought meant when I wrote that. Oh, yes. It's about deciding who can see what inside it. Authorization, authentication, all those sorts of things could be quite difficult in the lift and shift model, and I would argue it's more simple in the other one. But on the other hand, debugging and logging is either very easy or very difficult, depending on how you look at it on the left, on the middle, right? You need trusted admins because you need ways to look inside it. But you can use your standard model for logging if that includes a trusted admin role. On the right-hand side, well, you can design it in, but you need to think, whenever you're doing anything with CC, how am I going to debug? How am I going to log? Because it can become quite complex. On the other hand, lift and shift is pretty easy in terms of design burden. You take what you've got, you put it in a VM, which is a confidential VM, and it pretty much works, right? It's higher if you're designing for CC, but that's true for any new application. You need to think in new ways, and there are absolutely some off-the-shelf and open-source projects which improve matters, and I will talk about a few of those shortly. So I've got a couple of use cases that I want to give you. And it being 2025, I'm legally obliged to talk about AI, at least briefly, so here I go. So this is how I think of AI. This is which is very simplistic, obviously, and probably wrong, but let's go with it. So on the left-hand side, we have something we're going to train, and that involves a couple of data sets and a training model. And what we're going to do is we're going to put all of that in a TE. Good start. And we're going to create an attestation. And that allows us to say, you know what? That data set, the other data set, and that model are exactly what we used when I did that training. Nice, right? It's a useful thing to be able to do. Particularly when I create my inference engine and I include that attestation in the inference engine, which means that I can create another, stick with me on here, another attestation measurement, which allows me to talk about all of that together and to use that for things like communications security. Because what I've now done is to say that when that user queries that inference engine, first of all, their question and the answer have been secured. Secondly, that she can be sure that she's asking that inference engine and not another one. And what's more, that the answers she's getting have come originally from those data sets and that training model. We have a question. I have two questions. You first, sir, if I may. The question is, what's the difference between the two attestations? There may be other things in the inference engine that you're attesting as well, and you're attesting it at a different time. You can do multiple attestations, but you're using them for slightly different things as well. You may be using the one on the right for the communications, whereas you're using the other one for provenance, basically. So provenance is what you're, the property you're looking at. So you had a question as well?
Those four attestations are not meant to be the same. It's just cut and pasting for the slide.
There are two attestations. The one on the bottom, and they have slightly different blue colors, which isn't clear enough, and I do apologize. In other slides, I've changed the ones and the zeros, but I haven't on this occasion because I got lazy. And changing ones and zeros gets boring. Yes, I apologize for not having done that. Thank you for pointing that out. So what we've done here is basically have a multi-step process. We've carried trust through the steps. That's a good thing. Hold that in your mind. So the next one is financial collaboration. Almost like I chose this on purpose, isn't it? And so here we've got three different banking or financial things, and I've chosen different icons. I've done the job this time. And they have a collaborative application. Maybe it's fraud detection, something like that. And they all have agreed that what that looks like, and they've all looked at it, and they're all happy with it. And so what we're going to do is we're going to put that into a T, and we're going to do an attestation measurement. Because what can happen now is that each of those different banks can look at that attestation measurement and say, I know two really important things. Firstly, that what is in that TE is the collaborative application that I looked at before, because I've got a hash of it. Hashes are good. Two, I can be sure that when I talk to that, anything I put in there is going to be secured because it's in a TE. And if the collaborative application is done correctly, I'm also happy that no one can exfiltrate any data or information from there. So that means I am happy to put my data sets in there. And they can all work together, and they can spit out some data output to which we can add an attestation, which means that we can prove that it came from the places we thought it did. This is another really useful set of properties that we can use in true life. Here, we've got multiple stakeholders who are mutually distrusting. And so this is how I think of confidential computing beyond just isolation. When we start thinking about clever stuff we can do with attestation, sometimes we have multi-step processes, and sometimes we have multiple stakeholders. And if you have any use cases where this is the case, confidential computing may be useful for you. And what about the bottom ends where we have both of those? Things like Web3 or hardware or software supply chains, we have a bunch of mutually distrusting parties, but also we have multiple steps in the process. So some really interesting use cases there. I'm running out of time, so I'm going to keep moving, but please, we'll try and find some questions. Time at the end. So let's think about building new architectural patterns. You'll remember this slide, and it's there to try and encourage you to think, if I care about any of these questions for any of the systems that I am building or designing, then you should definitely be thinking about confidential computing and whether any of these properties would be useful properties to help you deal with the questions on the right. And these are some of the use cases where we're absolutely seeing such properties being useful. I won't read through them all. My favorite one, honestly, at the moment is cross-border multi-jurisdictional. There come some really interesting questions about, just because something is executing in country X, does that count as being actually in country X if it was set up by someone in country Y and it's fully isolated and only the people in country Y, or maybe people in country A and B, not Y, can look at it. So the jurisdictional questions around the cross-border or things around here are quite complex and still being looked at, I think it's fair to say. So here are some questions I think I'd like you to be going away and asking of yourselves and of your companies. You know, what is the threat model? What's the risk model? Who needs convincing of what information? Who are the attackers? What resource they have? And also who really needs access? Everyone wants access to things, but often they don't really need it. And maybe you can reduce the things that they have access to because you now have the controls actually to enforce that, which is much more difficult if you're just doing, database row management, for instance. So how do you get started? Well, there's a number of open source and proprietary solutions out there. Lots of the proprietary stuff is container-based because everyone loves containers. We're still in 2020s, so I have to mention containers and Kubernetes as well. And a number of them are targeting AI use cases, and some are lift and shift. So there's a number of options for you there. But I would also love you to be looking at the open source options, because open source is always best, yay. And they go from anything from complete frameworks through to sort of mini OSs and library OSs, attestation frameworks, many multi and cross architecture, so they will support maybe Intel and AMD and NVIDIA, for instance. Very interesting going on there. And you can find a couple of places to start there. Not everything is in the Confidential Computing Consortium, that is fine. The Confidential Containers project is based in the CNCF. Very happy to talk about that and their architectural decisions at some point if people would like to do so. But that's good. Oh, and the other thing is that most CSPs provide confidential computing. But do check whether it's hardware-based, because there's one provider who provides something they call confidential computing, which is not hardware-based. So that's it. I have 2 minutes for questions, or you can find me throughout the rest of the day, and I'm doing another talk in a bit. Any questions? I'll go with you first, if I may, sir.
I work for Confluent, it's a data streaming platform company.
Nice to meet you.
Question for you, what kind of adoption have you seen with this technology in the last few years? And then, as Confluent, a SaaS provider, how do you recommend we talk to our customers about technology?
So the question is, how much adoption have we seen, and how do I recommend that a company such as Confluent talks to their customers? The answer is adoption is growing very quickly, and people are very quiet about it, as they tend to be about security technologies. But we know that it's being used a lot, particularly the newer generations, the VM-based technologies, which have come out over the last 3 or 4 years and are now they're in the second or third generation, and that's really helped. And the fact that it's available pretty much everywhere is obviously hugely useful as well. How do you talk about it to your customers? WhatsApp recently did a big advertising campaign in just general media saying we can't look inside your conversations, and that is because they're using confidential computing. So I don't think customers really need to know or want to know the confidential computing words. It's not an Intel Inside kind of stamp particularly. It's about maybe talking to how you help their privacy, how you stop people doing things they can't do. It's about raising the bar, and that's how I think I'd talk. We have another question here, I think.
The Apple M-series ARM processors introduced memory tagging for something similar. Is that
So the question was the Apple M-series added memory tagging. I don't believe that they're using the ARM CCA, ARM 9 CCA capabilities. It's different. So no. I think we're done in terms of time. Yes, dead on. Please do find me through the rest of the day. Visit the Confidential Computing Consortium. Find me on LinkedIn. If you're here, your company should be thinking about joining the Confidential Computing Consortium. I'd love to speak to you about that as well. Thanks for your time.